So I'm going to go through an example of a multi-unit process where we have several unknowns that we're going to try to solve for. So this is a problem actually just taken from the book, an example from the book that I'm going to go through and walk through the logic and my thought processes as I work this problem. So we have this as a flow diagram which is given to us right here. So we're just going to assume that this information shown right here is given to us in the problem statement, and we can work from here. And we want to try to find out the flow rates and the compositions in streams 1, 2, and 3 here. Well, first thing what we're going to do is, we have our flow diagram, so we want to write out our variables, identify our variables. So what I'm going to do is I'm just going to write down right on the flow chart the unknown variables. M1, it's a flow rate, so I put a little dot there, and this is kilograms per hour, and that's in stream 1. And then we have X1, which is the mass fraction of A, and that's kilogram A per kilogram. And then I could write out X2 or X, another variable, but I'm just going to write this as X1 minus X1, and that's kilograms B per kilogram. So rather than writing out a separate variable for the mass fraction of B in stream 1, I've just written it as 1 minus X1 because I know they both add up to 1, and that just saves us a little on the variables that we might have to end up writing. Saves us a little effort on trying to solve for some of the variables that we will have on this problem. So the second part is M2, and this is kilograms per hour. Put a dot there. And then we have X2, and this is kilograms A per kilogram. And then 1 minus X2 is kilograms B per kilogram. So that's parts of stream 2. And then finally over here I have M3, that's kilograms per hour, and X3, kilograms A per kilogram, and 1 minus X3, that's kilograms B per kilogram. Now, these are all the unknown variables that we're trying to solve for, and I could have set this up various different ways. I could have written out, instead of in terms of mass fractions, I could have written out flow rates for components A and B, but the problem is formulated in terms of mass fractions. So it just makes sense for me to write out the similar variables, in this case mass fractions here and here, and all these locations, rather than individual flow rates. So overall, what do we have here? We have ourselves 6 unknown variables. We have M1, M2, M3, and then X1, X2, X3, 6 unknown variables. So we have to decide at this point what we're going to do to go about solving this problem. And this is where we start looking at boundaries, where we draw our imaginary boundaries, and we use that to help guide us as to what equations we'll write out and how we'll go ahead about solving them. So what I can do at this point is I can look at my boundaries, and I can use that to do some further analysis in the material balance equations. Particularly, I'm going to look at some degrees of freedom analysis, because that will tell me if the set of equations that I've derived from using boundaries and from material balances are actually solvable. So let's just dive into this. First thing I want to do is look at the boundaries on the overall system. This is the overall system here. So I just draw myself a nice little red line here, and I look at what's going in versus what's going out. So I have this stream here coming in, this stream here coming in, and then I have 3 streams leaving. And I can write out material balance equations on this. Before I do that, I want to do some degrees of freedom analysis. So I'll just do my degrees of freedom for the overall system, which is shown in red here. And so for the degrees of freedom overall, I have to compare the number of unknowns to the number of balances. In this case, I have two unknowns, so two unknowns. And if you look at what streams are crossing that red boundary there, you'll see that there's only two unknown values, and that's M3 and X3. There's two equations. Well, how do I know there's two equations? Because we have two different species in this system. So the number of species determines the number of equations that we can use, independent equations. So by doing that, I get a degrees of freedom 0. So that tells me that I can go ahead and solve this for the unknown variables, in this case M3 and X3. And we'll save that for just a little bit. We'll go about solving that. But I can go ahead. You can go ahead and do some other degrees of freedom analysis. So for instance, I could do some around the mixing point, in this case mixing point right there. And if I do that, degrees of freedom, I would have 4 unknowns, in this case M1, X1, M2, X2, 2 equations, for a total degrees of freedom of 2. So can't solve that. So I know, okay, I'm not going to do the mixing point. I can go ahead and do some degrees of freedom around this unit here. And if I go ahead and do that, I will get my degrees of freedom as 0, because I'll have 2 equations, because there's two species in this, but I'll have 2 unknowns, M1 and X1, so the degrees of freedom would be 0. I could do some degrees of freedom around this unit and try to figure it out. In that case, I'd find the degrees of freedom is 2, because I would have 4 unknowns, M2, X2, M3, and X3, but only 2 equations. And I would find out that the degrees of freedom is 2, so I can't solve it. And so we do this type of analysis to help us go ahead and decide where we want to start in these type of problems. So I'm just going to jump in and start trying to solve this. So let me just first draw my overall boundaries, my imaginary boundaries, and again I've already determined that degrees of freedom is 0, so I can solve it. So at this point I'm going to go ahead and just do a total balance on this system. In that case, what's going in versus what's going out. So I have 100 kilograms per hour plus 30 kilograms per hour equals 40 kilograms per hour plus 30 kilograms per hour plus M3. Well, this is just an algebraic equation. I can just go ahead and rearrange it to solve for M3 is equal to 60 kilograms per hour. And of course I want to put myself a nice little box around that problem, or that answer right there. I can do a balance on A. So A balance, again we're using the boundaries shown up there in red, 100 kilograms per hour times 0.5 plus, let me just draw a dividing line there, 30 kilograms per hour times 0.3 is equal to 40 kilograms per hour times 0.9 plus 30 kilograms per hour times 0.6 plus M3 multiplied by X3. Well, it may look like we have 2 unknowns, but we don't, because we have in this problem, we've already solved for M3. It's over here, so we really only have this unknown variable X3. And if we just go ahead and use some algebra do some, simplification here. That would give us x3 is equal to 0.0833. And that's the mass fraction of A in the stream 3 leaving the system. So there we have our answers right there. The next step that we want to do is look at where we can solve for the other unknown variables. And we can do lots of different ways here. We could look at Unit 2 or Unit 1 here, but I'm just going to look at Unit 1 because if you recall, I previously did some degrees of freedom analysis and it's 0, so I know that I can do my boundary around Unit 1 to solve for M1 and X1. So let me just continue on. In this case, I'm going to do a boundary around here. And so I have what's going in versus what's going out. And I can go ahead and do a total balance. In this case, 100 kilograms per hour is equal to 40 kilograms per hour plus M1. Well, now that means it's pretty straightforward to find out M1 from this equation. Sure, that's a 0. That tells us M1 is equal to 60 kilograms per hour. Put a little box around that problem, or that answer. And then I can do a balance on A. 100 kilograms per hour times 0.5 is equal to 40 kilograms per hour times 0.9 plus M1 times X1. And again, we know what M1 is because it's right there, so the only unknown variable is X1, so we can just go ahead and solve for X1. And if we do that, we get X1 is 0.233. Put a little box around that one. So there we have it. Now we've gone ahead and found M1 and X1 by doing the boundary around this unit here, what I call Unit 1. And we are almost done. If you haven't figured it out, we just have to find two more unknown variables, X2 and M2. And there are again lots of different ways that I can go about solving this, but I'm just going to do the analysis on that mixing point right there. And by doing that, I'll have the total balance, which has M1 plus 30 kilograms per hour is equal to M2. And that's just, again, what's going in, these two streams going in versus what's going out. And this is just a straightforward equation because I know M1, I found it over here, and I can solve for M2, and I get M2 is equal to 90 kilograms per hour. And then if I do my A balance, M1 times X1 plus 30 kilograms per hour times 0.3 is equal to M2 times X2. And again, we know everything in this equation. We know M1, X1, and M2. We just don't know what X2 is. So we can go ahead and solve for X2. X2 is going to be 0.255. And again, I'm going to circle that answer. And that's it. We've solved for all our unknown variables. And just to recap, we looked at this and we did some degrees of freedom analysis around different parts of this. Big part of it was drawing our imaginary boundaries around different parts of this process, this multi-unit process, in order to identify material balances. So again, I could have drawn, a material or imaginary boundary around this unit, over all the whole system, whatever. But by doing that, we can identify different equations, and it helps us narrow down sets of equations that we can use to actually solve the system by combining the degrees of freedom analysis with our imaginary boundaries and then using those equations to actually solve it, just like I've done for this problem. And there you have it, the solution to this problem. And this is more or less how we solve all our multi-unit processes. We have to do a systematic approach where we choose parts of the whole entire process to solve, and then from that go to other parts of the system to solve it and do it again in a systematic way.